let's do something a little different. Rather than focusing on comparing items to each other as a whole, we can look at some of the features and parts of our data and use it to sort in more creative and hopefully faster ways. So we saw that our best comparison-based sort was O of n log n. We can't do better than that if we're comparing items to items. So we have a lower bound on the worst case behavior of comparison sorts. But if we sort without using comparisons, we might be able to try different approaches that get us there faster, surprisingly. So the comparison-based sorts that we've looked at don't assume anything about the data that we are sorting. If we limit some assumptions about our data, then we might be able to do a faster sort in that way. For example, if the range of our data was limited, we're often looking at a small range of things, like the scores on a test always fit into a range of 0 to 100. The ages of people are pretty limited. The indexes into an array, if the array is of some reasonably small size, are also a pretty reasonable thing to handle. Even things that have many digits or many characters to them might still fit a relatively small range between the lowest possible one and the highest possible one. So if we can assume that there's some range m that all of our data fits into, and that m is linear on the order of n, then we can do really cool things with it. So if we have some constant, we could multiply by n being the number of our items, our data items, that gives us the range that we're looking for. Then we can sort those items into buckets to hold the keys. So in the case of simple integers that you don't need to store, say, a student record along with that integer or anything like that, you're just storing the number, you can in fact even make an array where each index in the array is the key that you're trying to sort. So someone's student ID number, or I'm sorry, that would be bad because you'd probably want the student record. Some number of the temperatures that you're trying to sort, or that kind of thing. Then you can use the value as the index into that array, and whenever you would have indexed that array, you increase a counter there. And at the end, you'll have all of the counts of which numbers need to be repeated how many times. Otherwise, you might need to use something like a linked list to actually store both the key and its associated value. When each element gets added, you sort it into the appropriate bucket for that given key. You increment the counter if you're using counters, and add it to the list if it's something more complex than just a simple integer. And then you create a sorted array by walking through each of the buckets in order. If the buckets are in order for the sorting order that you're trying to do, then you can walk through each of those buckets and you can just grab out the items that fit into that bucket and put those into sorted order. Putting something into a bucket is O of 1, for example, in the array situation. Doing the index is not too big of a deal. Or we can use a hash on some data and therefore use the hash value as an index, compile that data down to just a small integer that we then can use that as our index in an array or into our data structure. Regardless of that, we're doing an m-way comparison in one step. We're putting it into the right one of those m buckets in a single step. This reduces our decision tree from the example before to a single layer with m leaves. So as long as those buckets only hold a single item there, whether it's that count or whether it's the real data, then we reduce our tree down by having a situation where we put them all into the correct buckets. If a bucket is empty as we walk through to get things out of it, then we don't have to do anything. And if the bucket contains an item, we put that item into place, and it's now in its correct place in the resulting list. If it's counts, we put however many of that item into our resulting array or list, and then we keep doing that from bucket to bucket. So we find that bucket sort is O of m plus n. It's O of n to insert all elements, because inserting a single element is O of 1. Therefore, to insert the n elements is O of n. And then to walk across the buckets, we have to do that. For the m buckets, we'll have to copy out our n data, so it's O of m plus n. If m is on the order of n, then bucket sort is O of n, because this m here is just another n. It could be 3n, it could be 1000n, but we know that 1000n plus n is 1001n, and that coefficient will go away in our analysis. So it's fine. It's O of n. That's great, actually. And this algorithm is stable. It will keep tie breaking from the original data, but it can't be done in place. You need the buckets for it, so you're going to need some extra memory. If we have a very large range, like if our m had to be larger than 1000 or larger than 2 to the 16th or 2 to the 64th, then we're going to need to break the data down even further, because creating that many buckets could cause us big problems in terms of memory, and we don't want m's that are large. Even if they're still O of n, we would still like to have some smaller m's if we can on that. So what we can do for larger data is we can use a bucket sort for each digit or each character if we're dealing with strings, and use the result of one of those bucket sorts as the input into the next. This kind of technique has been used since the 1890s for census results and being able to sort those and organize those, and doing punch card sorting where data for computers was stored on punch cards through much of the 20th century, early computing for us. This algorithm of putting things into bucket sorts and then repeating that bucket sort on the next digit or next character is called Radix Sort. We set the number of buckets to m, and this m will be our radix for our digits or for our characters. The radix is the base of a number system, or the number of distinct symbols. So for decimal numbers, that would be 10, and for alphabetic characters, that would be 26. Even for the ASCII table, there's a limited number for it. So we can create a bucket at each iteration for that character or for that digit. We'll do a least significant digit version where we look at the least significant digit first, then the next most significant, then the next most significant. We do a bucket sort for each digit, and we end up with our last sorting step being for the most significant digit. Since there are multiple keys in each bucket as we do this, because there can be multiple keys that have the same ones digit or tens digit or whatever, then the buckets can't be counts. Here's an example that will perhaps help to clarify this. I've got this data here. It has a radix of 10 if we do decimal digits, and it will require 3 steps because it's got 3 digits for the character, or for the numbers, at most 3 digits to them. In the first pass, we'll sort on the ones digit. So you can see the zeros got shifted into the 0 bucket. If I were to draw the buckets, that bucket would be of size 2. The ones got shifted into the ones bucket. There is nothing in the twos bucket. There's only a single item in the 3s, 2 items in the 4s, and there's nothing for any of the other buckets past that. So if I did have these sorted into separate buckets, as I walked through, I would grab the 40 out and put it in my result array. I would grab the 350 out and put it in my result array, and then I would step forward to the 1 bucket and grab these items, and so on. That, of course, didn't sort our data, but it got us started. Then we sort on the tens digit. So you can see that the 4 with only a single digit is treated as 04 and put into the 0 bucket. And it's already in its correct end location because it's the only single digit item and it's smaller than all of the others. So these two, 21 and 40, are accidentally in the right order now. Oh no, they're actually by design in the right order now because they have a 2's digit that's in the correct place. I'm sorry, it is accidental because currently we're putting them into buckets on the 2's. In the next step, they'll be correctly in the order because they got sorted into the 2's bucket in this step. I'm sorry, the 10's digit bucket of 2 and 4 in this step. And then in the next step, we'll shift everybody into buckets based on the 3rd digit. So here, this one got placed here because of the 5 in the 10's place. This one also got placed into the 5 bucket. So you can see they're grouped together now, and they won't be in the next step. 6 bucket, 8 bucket, and we've got several empty buckets. Then when we sort on the 100's digit, we have all of these go into the 0 bucket because this is 004 and this is 021 and 040. They are already ordered now for their final location. So are all the rest because 3 is the largest digit that we have in this data that we've seen here. So this has 1 for its 100's digit. These all had zeros. They stay in the same bucket. This is alone in the 1 bucket. This is in the 2 bucket. This is in the 3 bucket. This is in the 5 bucket. And the other important thing you can see is that when there are ties, as in all of these had zeros, the order from the previous sorts is kept. So it keeps the 4, the 21, and the 40 in the correct order as they're put into the 0 bucket for the 100's digit. And that's what keeps us sorted. And if we had something else that had 100, 170, or something like that, it would have come from the 7 bucket and therefore would have been further out, would come after 154. So to do some analysis about it, we know that each step of doing this bucket sort is O of m plus n, where m is linear in terms of n, so it's similar to an n. We pick our m so that we know the number of passes we have to do, p, is constant. The number of iterations that we have to do will be constant. In the previous case, we knew the number of iterations would be 3 iterations through the data to have it finally sorted. If our data had 20 digits, p would be 20. The extra storage that's required for this is relatively minimal. We're only going to need to set up those buckets. So we may have some empty buckets. That's a tiny bit of wasted of information, but it will be m buckets for it. And we will have to put our n items into those different buckets. So the running time for this is O of p times m plus n. And to break that down, since p is a constant, we get by multiplying in pm and pn. So we know m is linear in terms of n. It could be 1000 n. Fine. That's 1000 pm. 1000 and p go away. M becomes an n in our big O type of notation. And n plus n is still O of n. So the final result of radix sort is O of n, with these constants sort of mixed in there that we might care about in real-world application. But in terms of our analysis, it's O of n. And each pass is stable, but not in place. Bucket sort was stable, but not in place. We needed the buckets for it. So radix sort is stable, but cannot be done in place, meaning it will need some extra memory for it, but it will keep tie breaking from whatever the order was previous to our data being sorted. So to look at an example of radix sort, if we sort 1,000,000 64-bit integers, we could use a radix of 2 to the 16th, meaning that our buckets would hold from 0 to 2 to the 16th minus 1 and then to the 16th, so on outward for each of those buckets. So that gives us about 65 or 66,000 symbols per digit or per the buckets that we're going to use in those. That will only require 4 steps on 64-bit integers, because 64 divided by 16 is 4. So that will give us 4 steps. Our P will be 4. Each step is about 2 million operations to do the placements and the copies. The whole algorithm is about 8 million operations. If we compare that to our typical n log n behavior, then the log part, log of 1 million, will be about 20, but the whole operation is about 40 million operations to do both the comparisons and the moves. Those are the 2 steps we have to do, for example, for merge sort or quick sort or that kind of thing. And so we will end up with a much bigger number of operations, 40 million operations, compared to Radix Sort's 8 million operations. So if we go outside of our standard way of thinking of comparing items to other items, we find that we can break out of this limit of n log n in our comparison sorts, and we can use things like Radix Sort or bucket sort that are O of n. They do make some assumptions about the data that you would want to make sure are true about the kind of data that you're sorting, but they can be done in O of n time if those assumptions are true.